So hello and thank you for joining this session, Newbie's Journeys to Vitess. My name is Igor and I recently joined MySQL in their enterprise support engineering team. With that, started learning about Vitess, and this session is just showing the learnings and how you would see Vitess as someone who's just started. So it's not something really advanced, but if you have advanced questions, I'm sure in the audience there are people that can take that. So yeah, a little bit more than 20 years in IT experience, mostly worked in the past 15 years with MySQL or MongoDB, and on a personal note, husband and a father.
I'm Matthias. I did the same thing as Igor just 4 years ago. So I'm now 4 years into Vitess. So I'm a little bit more advanced, but I have kind of the same background Igor had.
Okay, so we will start by discussing some of the MySQL limits that exist, running online DDL, query management, high availability, disaster recovery, vertical scaling, horizontal scaling, and how Vitess solves, if not all of this, most of this. Starting from the beginning, probably how most of the applications are being deployed initially, just the application talking to a single database instance. That single database instance can grow vertically. I tried to do some research about what would be the largest instance that money can buy. Today that's showing that like 8-socket CPU with 60 to 144 cores per socket, 32 terabytes RAM memory. Translated into money, that would be like €500,000 without disk. So adding NVMe on top of that would be maybe in the range of millions. MySQL itself doesn't have limit on database size. The database size can grow basically indefinitely. The actual limits come from the physical limits on the instance itself. Table size with the default 16 kilobyte page size can grow up to 64 terabytes, or if you configure the page size to 64 kilobytes, the table space can grow up to 256 terabytes, and that's just for a single table. Max connections is
unless partition.
Unless partition.
Because which partitions?
Right. Okay. The max connections limit is 100,000. Probably not all of those can run concurrently, so the threads running is definitely something that will not scale to 100,000. And big integer, for example, is a row, the number of rows, how many it can store is 18 quintillion. So that also depends on the row size, but is a number that's the largest. As the applications evolve, obviously there should be some safeguards on the database. So things like MySQL already has optimizer hints, and we can set max execution time, but also things like if the application runs a query select star from users, and the users is very large table, you want to safeguard the database and add limit that here are the first 10,000 rows, or even if you want to set a default query timeout, time out the query after 5 seconds, but you can have comment directive where you say this query timeout should execute on 100 milliseconds or even after 30 seconds. So customization on that. Something that was already mentioned in the talk from Matt today, query consolidation is also something that's useful if you have a bunch of queries that come to the database at once and all the queries are selected from videos where ID equals 1. It will not run all the queries, but it will consolidate, and by just executing once on the database, it will return a result set to all the connections. The next big challenge in MySQL is running DDL. A lot of progress is made by doing some of the changes instant, and also there is online DDL, but it's still challenging to alter very large tables. There are tools like Reckonal and schema change, Ghost, Spirit, that basically work in a way that the original table is not altered, but a copy of the table is modified, and then that table is being populated by copying the rows from the original table. When that is in sync, a brief log is taken, swap the tables, and then the change is applied. However, none of those tools, maybe Ghost has that latest feature that it can resume on failures. So if that operation fails in the middle, the changes are lost, so hours, days of work are lost. And even if it doesn't fail, there is no easy way to later revert the change. So we are modifying a column, we are not happy with the change afterwards, we want to go back. So that's also something that's challenging with the MySQL deployments today. Another thing, migrating data from one server to another server, one region A to region B, we want to migrate the entire database, or we just want to migrate a subset of the data. We have to replicate the data, catch up with replication, then the application has to atomically switch all the writes from region A to region B. But if we identify again that something's wrong, we have to go back. At the same time when we switch, we need to replicate all our changes from region B to region A. And flexibility where we can first switch our reads, warm up this region, or just send a percentage. So all those things are challenging for the application, and it does require additional orchestration. Not all deployments can run on a single node. Obviously, we need to consider high availability as part of the deployments. So things like the application should be aware, where is my primary, but at the same time, if we're using replicas for reads, then the application has to have into account what is the DNS where I send my writes, how do I split my writes, whether it's round robin, what replicas are eligible for reading. If our replication lag goes above certain threshold, we should stop reading from that replica, or if all of the replicas are lagging, then we have to have at least some minimum number of serving replicas so that the application doesn't experience downtime, as well as all of that should have disaster recovery in mind. So if it's deployed in region A, B, and C, we should have some tolerance where a single availability zone can go down and it doesn't affect the deployment. The application also should be resilient, that if the primary is down, then one of the replicas will be promoted as primary. At the same time, the engineering about this is to take one of the replicas as primary, but at the same time rebuild the former primary, so it will join the cluster, and there will be the minimum number of nodes as configured. At this time, the application will experience errors if the primary dies and the application is directly connected, unless the application has some buffering where it says that the primary is down and it starts buffering the request, and by the time a new primary is promoted, then all those requests will be taken to the new primary. And additional feature that the application can have in this case is when a new replica is joining the cluster, that new replica will just serve a portion of the traffic, so it warms up by the time that the application can hit that replica with 100% traffic. We are not hitting a cold buffer cache, so just to reduce the overall latency in the system. And this can work. MySQL has come along, though there is InnoDB replica set, there is InnoDB cluster where this can be synchronous replication, or semi-synchronous also can work. To remove the complexity from the app, all the backend can be behind a router, so the router is another part of the application, or separate application that takes care of where is my primary, where are my replicas. And of course, this also needs to be in a highly available setup, so that when the router goes down, we don't experience the same downtime. And this is the most complicated setup maybe with MySQL today. High availability, disaster recovery, everything in one solution. The cluster set, I think it's, yeah. But still, this is the primary that takes all the write workload, and that's where the application is hit by the bottleneck of having to vertically scale this instance to be able to handle all the workload. Now, the next thing is scaling vertically by maybe adding more instances when we have to scale our read capacity. As the workload increases, we can add different replica types. For example, we want our all-up workload to work, to just be hitting that replica, and we don't want our other replicas to be impacted. Or we want to have a dedicated replica we take the backups from, or we can even have intermediary replica where behind that replica we can have additional scaling for our reads. So that there is flexibility on that, but that adds to how long the backups will take, that adds to how long we will restore. The DDLs will run longer, and we have log contention. As we scale vertically, by adding bigger and bigger machines, the costs grow almost exponentially, and we don't even get linear performance gains. So this solution doesn't really work very well. Something that might work well is if we split our databases by, let's say we have our database for users and user metadata at one cluster, and our commerce database in another cluster. So in this solution, the router is where all the intelligence lives. The application sends queries. I want to query my user's database. The router knows how to route the queries, and it gets update from the application. If something changes in between, a primary gets promoted. The same as with the commerce. It adds complexity because we may have a normalization that we have to query the users and the commerce at the same time, so there will be join in tables that are going cross shards, if we consider this as two separate shards, and as well as referential integrity between the databases. And the next thing, the commerce database grows so much that we have to start splitting the commerce database. So maybe if we're tracking orders from 1 to 1 million, it's shard 1. From million to 2 million is shard 2, or depending how we want to split the data in different shards. And again, the complexity is in the router, because now it needs to keep track, where is my commerce shard 1, what is the primary, if a primary fails, needs to update, and we need to keep a metadata where the primary lives, what are my replicas, if I want to query order 1 million, what is my shard. So that all that complexity is in the router, and the metadata needs to be up to date. And we have to have the limits where we select star from a table. It needs to have some automation that we cannot just get all the data from all shards, because that will overflow the network, and it's just the application will not get any results yet. And the next thing to horizontally scale is we have to have this process of how do we split all of these shards so that we know where is our data. For doing that, every single MySQL instance needs to have a process that controls that instance, and a process that is basically communicating with the router, updating the metadata, and the router knows, okay, for shard 1, I know what is my primary, where are my replicas. When I send a query, then this process that controls the MySQL instances on the backend knows how to limit the result set, or if it needs to consolidate a query. And we end to something like this, which should be called a Vitess cluster. So the Vitess cluster, what it has, every shard has high availability of one primary and at least 2 replicas. The processes that control the MySQL backend are called vttablet. And vttablets are managing the MySQL instances. The routers in the middle, it's called vtgate. Those are stateless and communicate with the metadata server, which is a topology server. That's where the topology of the entire cluster lives, and it gets updated if something changes. So primaries can fail, replicas can fail, new nodes are being spun up. So all those changes in the cluster, those are updated to the topology. As the data is inserted from the application, it will get a shard key, and based on the shard key, it may live to shard 1 or shard n, so that the router knows what are the ranges in the data, and it knows where to send the query. And usually this lives behind the network load balancer, so the application connects like it's just a single MySQL connection, and all the complexity for everything is just on the right side. A more advanced architecture is this one, and Matthias will take over.
So this is the architecture slide that Sorry, there's a question.
You talked about the topology server being the database also. Is it the MySQL also instance, or is it?
Yeah, I think.
No, topology server in Vitess is always either etcd server or Zookeeper, or in some cases still console that's supported, but that's been phased out as supported. So by default, you will run an etcd server as your topology service. So this is the official Vitess architecture slide that Matt also shared this morning. So you see here each of the shards. It's a normal MySQL cluster, like primary replicas, all types of replicas. Just each of the MySQL D processes has a sidecar called vttablet to be able to communicate to the rest of the Vitess components. The topo server is on the side here. It's very important for Vitess, but it's not in the query serving path. So if the topo server would go down, it's still able to serve queries, but you are not able to do any changes to the cluster anymore. vtgate is the component that translates all the queries that come in to queries per shard. And it tries to utilize the features of MySQL as much as possible. So if it can push down joins to the MySQL layer, it will do that. Go next slide. So these are some of the logos that use Vitess in production, some very famous ones. Some key concepts in Vitess land. A keyspace is the combination of a logical domain, like Igor mentioned, the users and the commerce. That could be two different keyspaces. The users has a set of tables that join together, and the commerce has a set of tables that join together, which makes it easier within the same key space to make those joins. A vtgate could do cross key space joins, but that's not going to be pushed out to MySQL then, so that's always going to be slower. And a shard is then the smallest segment part of a key space. The minimum number of shards is 1. So you only have one shard, unshard key space we call that, but you can have any number of shards that you want. And the topo server we talked about already. So Vitess provides your application an illusion, like if you connect, it would look like you have one large database. Each key space would show up if you do show databases as a different database, and then if you show tables from each of the key spaces, you will see the tables that are there. It supports MySQL 8 and above. It's used to support 5.7 as well, but since that's already end of life, and we're going to 8.4 now, we're not talking about it anymore, and it looks like a single dedicated connection, while in fact you might be querying hundreds of servers. Vitess needs to deal with all these third-party things and frameworks. And that brings us to vReplication, which is a very important and useful feature in Vitess. vReplication is used for these three big items, like if you want to import data into Vitess, you do a migration. If you want to move data around or reshard your data, you can do that as well. And if you want to improve query performance by like pushing down a table to different shards, like if you have an uncharted table, small one, that you want to push down as a reference table. The example that I always use is a currency table. If you have a web shop and you want to show the results in the local currency, the currency table is probably very small, but you can materialize that on each of the shards, so you can join on MySQL level with it. And then how does the vReplication work? Basically there's two phases. There's a copy phase and a replication phase. Copy phase basically runs select star from table and starts streaming the rows in the primary key order to the target. It keeps track of the last copied primary key because by default it only runs for 1 hour, and then it goes to the next phase, and then it will iterate again until it copied the entire table. This is to prevent that you would copy for 5 days and then end up in a situation where the binary logs have been already purged and you cannot catch up anymore. So for doing an import workflow into a Vitess cluster, you would have an existing MySQL topology or server somewhere, and you would point a vttablet to that server, and you call that an external key space, like it's a Vitess component, but it's not managed by Vitess itself, the MySQL data that's in there. So it's to Vitess as an external keyspace. Then you create a Vitess keyspace in your cluster, and then there's a command called move tables that will create a vReplication workflow to move your data from your existing topology into Vitess. It does that in the 1 hour segment, so if you have small tables, one table can go in one go, but if you have very large tables, you will have the iteration of copy phase and replication phase for many days. And then once the data is all moved into Vitess, this replication workflow just keeps on replicating until you decide to do something with it. We can also verify that the copy is the same using a vdiff feature, which will basically run a diff on runs a checksum on the records in the both sides and compares the checksum to see if the data is actually binary the same. And then you can switch the traffic to this new replication, this new keyspace, by doing switch traffic. You can switch the read traffic by the auto traffic targeting the replicas. If you do that, you will just start reading from your read replicas on the Vitess side, but you still write on the original side, and the replication still goes to your new cluster. At the moment that you press the switch write to start writing to Vitess, what Vitess will do is it will reverse the workflow direction. So now you start writing on the Vitess primary, and you will be replicating back to your external MySQL, so you have a rollback path in case you have any issues. And that's the most important way that schema changes work in Vitess. Alter table issues, we're all familiar with that, we're all MySQL people, so we all know what the problem is. And so if you do a Vitess migration, you can set your DDL strategy on vtgate to online, and you just run your alter statement, and it gives you back a UID of the migration created, and it will start the workflow under the hood, like we saw before, creating the copy table, moving all the data over, replicating. You can switch the reads, switch the writes separately, and it will be able to revert as well. And then you can follow the migration by just showing show Vitess migrations, and you can see then where it's at. So this statement is running. My migration was complete here. And as I said, you can just revert the replication because that workflow has been turned around. And if you see like, oh no, this migration doesn't do what I expected it would do, you can just revert your migration. It will flip the workflow direction, and so you can then write again to the original table without any data loss. Finally, there's also declarative migration, so if you don't like to write alter statements, you can just change the schema. You say you want to do online declarative, you recreate your table. It says, okay, I will do that, and it will figure out the differences that it needs to make. So, yeah. Conclusion, schema changes are back in the hands of the developers. It's easy to run, easy to revert, and vReplication is very robust, so it can even survive the failover of a primary of all the